Hey, welcome back to Fat Mama Physics. In this video, we are going to do a very long IB style question, kind of like before. This one here is has to do with a charged particle moving through a uniform electric field. Before doing this question, you should really know how a charged particle moves through an electric field, as well as a magnetic field. So probably something like an end of topic question. So this is one of my favorite questions. It pretty much takes, it applies everything, it applies a lot of things you learn in this unit, as well as tying in units that you've learned before as well. So without further ado, moving my mic closer, let's get started. Woohoo! This question is about motion of a charged particle in an electric field. An alpha particle of mass 4U, and U is for, think of U as a nucleon, kind of like either a proton or it's a mass of atomic particles. So in your data booklet, you can look it up here. It's called a unified atomic mass unit. So it's the average mass of a proton and a neutron, essentially. So here is 1.661 times 10 to the power negative 27 kilograms. So it makes sense because an alpha particle is made of 2 protons and 2 neutrons. It also has a charge of 2e, which is 2 elementary charge, which is 2 protons. It is accelerated from rest in a vacuum through a potential difference of 2.4 kilovolts. Show that the final speed of this alpha particle is 4.8 times 10 to the power 5 meters per second. So very nice juicy question here. So it is a so let's define a few things. First of all, let's define the charge involved. The charge involved is going to be 2 times our elementary charge is 1.6 times 10 to the power of negative 19 coulombs. We also know the mass here. The mass is going to be 4 times the 1.661 times 10 to the power of negative 27 kilograms, which is the unified atomic mass. And so it starts off from rest, meaning that we have initial velocity of 0 or we have kinetic energy of 0 at the very beginning. Okay, we know that the work done on a charged particle is equivalent to the electropotential difference times the charged particle itself. And this work done by the electric field is going to cause the alpha particle to gain kinetic energy, and this kinetic energy will just be the final kinetic energy since the initial kinetic energy there is 0. Okay, so kinetic energy we know is 1/2 mv squared. V is the speed, which is what we want to show. Okay, so essentially we have this VQ is equal to 1/2 mv small v squared. So let's do a bit of algebra just to solve for this v here. Dividing both sides by mass, multiplying both sides by 2 is going to give us v squared equals to 2 VQ over m, and then ultimately taking the square root. This is going to give us v is equal to the square root of 2VQ over m. And so let's substitute everything inside. We're going to get 2 times the potential difference. This is 2.4 kilovolts. And the charge is going to be, don't forget, that's 2 times our elementary charge, 1.6 times 10 to the power negative 19 coulombs, and over the mass, which is 4 times 1.661 times 10 to the power of negative 27 kilograms. Okay, so then we have that. Let's put in our calculator. Okay, and the final answer I get is 4.808 times 10 to the power of 5 meters per second, and rounded up to 4.8 times 10 to the power of 5 meters. Let's just show it using the IB method. Okay, with the est to the power negative 1 for the inverse. Okay, so there you go. That was the first question. Whew. So we are going to assume here this alpha particle is traveling in direction parallel and midway between 2 parallel plates. So it looks like this alpha particle is accelerated to the speed of 4.8 times 10 to the power of 5 meters per second before it goes through another set of parallel plates. But the direction of these plates are up and down. So if you have a positively charged alpha particle going here, then of course you're going to experience electrostatic force that's going to push you down towards the other end of the plate. The electric field is going to go down, and so an alpha particle will actually bend towards the other part of this plate. So it's going to get shot and it's going to bend in that direction. Kind of like a 2D projectile motion question, if you think about it. Okay, so I'm going to save that speed there. Might use it later. Okay, next question. The metal plates are length 2.4 centimeters, so that's this length here. Their separation's 0.8 centimeters. Potential difference is 600 volts. The electric field is uniform in the region of the plates and zero outside of it. Calculate the magnitude of the electric field between the plates. So, very standard question. So the electric field, and it's because it is uniform, the electric field between the two plates is going to depend on the distance, the potential difference between the two plates divided by the separation between the two plates. So that's 600 volts divided by 0.8, and don't forget this is centimeters, so I'm going to multiply this to the -2 to get it in meters, and which this is going to give me 75000. This I can either use volt per meter, or I can use Newton per coulomb. Either of these will work. So I'm gonna write that one there. Okay, so I've now have the electric field. Okay, next one, show the magnitude of the acceleration of the alpha particle by the electric field is this much, very high. Okay, so what that means is, as this alpha particle is entering this electric field, it's going to experience electrostatic force towards the other end of the plate. So this electrostatic force is going to depend on the electric field, and we know that it depends on the electric field via this relationship. The force is dependent on the field times the charge, meaning that the greater the field, the more force the charge will experience. The greater the charge, the more force the charge will experience. It comes from this definition. The definition of the field is the force acting per unit of charge. Okay, so that's where that definition comes from. Oopsie. Okay, so let's use this to find the force, because we know the electric field from the previous question. We know the charge is an alpha particle, so that's 2 times the elementary charge. And from from the force, we can use that to find the acceleration from F equals to ma. You know what? Let's do that right. Let's just equate that right now. Since that's the only force acting on the alpha particle, this will just be equal to the mass of the alpha particle times the acceleration. And to solve for the acceleration, we just have to divide the other side by the mass. Okay, so acceleration, we're going to get this as the electric field times the charge divided by the mass. So the field from the previous question was 75,000 volt per meter times the charge, 2 times our elementary charge. Okay, and then the mass is going to be 4 times the unified atomic mass, since we have an alpha particle. Okay, and putting all this in. Okay, a little bit squishy here, but I'll write black instead. 3.6 times 10 to the power of 12. And this is going to be meters per seconds, or meters to the -2. All right, there you go. That was double I. Okay, next one is CI. Calculate the time taken for the alpha particle, whoopsie, to travel a horizontal distance of 2.4 centimeters parallel to the plates. This question is not very clear that this alpha particle is about to be sent through these metal plates. It kind of assumes that you're going to make that connection. It doesn't make that very clear. So you just kind of have to, how would you do that? I mean, first of all, you kind of have to be careful. A lot of students fall into the trap that they now have the acceleration and they're going to try to use that distance to find out the time. But be very careful. This alpha particle is being accelerated downwards, okay? It's accelerated downwards. It needs to... You want to find the time it takes to go across the plate, not the time it takes to go to the bottom plate. It has to go through the plates, the time it takes to go through the plates, okay? So, in order to do that, you kind of need this speed that you got in the first part of the question, which, yes, IB is really tricky, likes to, like, it really forces you to use every part of the question possible. So, be careful of that. And, so how do you tackle this? Think of this as a 2D projectile motion. This alpha particle is getting shot horizontally. Imagine this is kind of like where you have a cannonball getting shot off the cliff at directly horizontally, and it's going to make a trajectory that looks like this. And it's this horizontal velocity here is always going to stay constant, assuming no acceleration in the horizontal direction. But because there is gravity, this particle is going to bend downwards, just like there is an electric field causing your particle to accelerate down to the bottom plate, for that matter. Okay, so this speed over here, this horizontal speed, is going to determine how far it travels horizontally. So that is basically the time that the particle will take to move across to the other end of this plate. So the 2.4 centimeters, essentially. So we're going to use this constant speed, and with this distance it has to travel to figure out the time there. Okay? So knowing that, this is going to be v is equal to distance over time, and the reason why I'm doing this is because the horizontal speed is constant. It's not going to be affected by the downwards acceleration due to vectors working independently of one another. So review kinematics if this is not making sense to you. To rearrange, we're going to get, we're going to need t. So that's the time is going to be equal to the distance it has to travel over the v. So the distance is 2.4 centimeters, 0.024 meters, divided by that huge whack of that velocity being how much again? 48. Okay, yeah, 48. I'm going to use the one on my calculator. 480,818 meters per seconds. So that is going to give us 4.99. 4.99 times 10 to the power of negative 8 seconds, which is going to be roughly 5.0 times 10 to the power of negative 8 seconds. Okay? And then finally, use your answers in B2 and C1 to deduce whether, as the alpha particles pass between the plates, it will hit one of the plates. So in order for this alpha particle to not touch the plate, it has to successfully move through the plates so that the trajectory might look like this. Woo! It go like, so hopefully like that. Meaning, if we know the time it takes the alpha particle to go across these plates, we need to see where it's going to land up, how much of a vertical drop it's going to make. So we will be, okay, so we know this alpha particle is shot midway between the two parallel plates. So it's exactly between here. So the half of this plate is going to be 0.4 centimeters. So if this alpha particle is going to take some amount of time for it to move downwards, whatever that time was 50 nanoseconds was what we found in the previous question. So in 50 nanoseconds, will this alpha particle move further than 0.4 centimeters, or would it move less than 0.4 centimeters? If it moves less than 4.4 centimeters downwards, it will make it across the plates. If it moves more than 0.4 centimeters in the vertical direction, it's going to hit the plate before it's going to be able to escape it. So the time that we got in the previous question will help us determine how much of a vertical drop it will make. So let's do that first. So to do that, we need the acceleration, which we found earlier, so 3.6, and as well as the time. So using our knowledge of kinematics, there's going to be the horizontal velocity, which we found earlier, and which means that there is no initial speed going downwards. So imagine that as the object is moving across, it's going to basically fall due to the electric field. So it's going to fall from rest. So it's kind of like free fall. So the free fall, so there's actually no v. It's going to go like this, meaning that if we have uy is 0, okay, we know the acceleration, we know the time, then we look at our, and we also need to know the vertical drop. So we need to know what that is. Looking back in our kinematics equations, this is going to be the one that we will use, 1/2 at squared. And we know u is 0, so we don't have that term. We just have 1/2 at squared. Whoopsie, there's a square there. Okay, so if we use this to figure out the vertical drop, we can see whether or not that is greater or less than 0.4 centimeters. Putting everything in, we have 1/2, the acceleration being 30, oh, it's up there, 3.6 times 10 to the power of 12 meters per second squared, and then the time being 50 nanoseconds, or 4.99 times 10 to the power negative 18 seconds. Oh, sorry, negative 8 seconds, not negative 18. Negative 8 seconds squared. Okay, so let's do that. Okay, so I get 0.00448. Okay, so this is essentially 0.448 centimeters, which is greater than 0.4 centimeters, meaning, therefore, it will not make it to the other side. Okay, so that's how you can show that. Of course, this question could continue asking you, how far does it make it before it hits the other plate? So, you know what? I'm going to put 2 bonus questions here and then make it a pause. I'll pause it and then I'll ask you to answer the question. So I'm going to do mention insert and then do it after. Okay, perfect. Okay, so here's my question. So give me a chance to type it out. Mwahaha. All right, so I made 2 bonus questions. So let me just give you some context before I let you run off with them. Here we go. How far does the alpha particle make it before it hits the bottom plate? So here is the diagram again, looking my ugly drawing here. So this alpha particle is, we know, will be subjected to electric field. It's going to accelerate towards the other end of the plate. The question is, if it's shot through the middle of the plate, how far along this plate will it land before it hits the bottom plate? So it's probably going to be less than 2.4 centimeters because we know it can't make it across the other end of the plate. Okay, so that's the first question. Here, let me draw a diagram just to help you out. Okay, so that's the first question. How far does the alpha particle make it before it hits the bottom plate? Then the next question here, you have a magnetic field which will be applied in the section of where the parallel plates are, so that this alpha particle moves exactly straight across the plates without any deviation in its path. The question is, what must be the magnitude and direction of this magnetic field in order for this alpha particle to move straight across? Okay, so guess what? Good time to pause the video before I go over the question. Okay, so I'm going to start with the bonus question A. And before we do this one, we need to know a few things. We need to know the acceleration. The acceleration is 3.6 times 10 to the power of 12, I believe, meters per seconds of this alpha particle. Okay, we also know that it is shot at 0.4 centimeters from the bottom of this plate, because the whole plate is 0.8 centimeters of separation. We also know that it is shot with a velocity of, before it was accelerated at the velocity here. So this initial horizontal velocity, which I'll label it that, or that, it doesn't matter because it stays the same, 480,818 meters per seconds. Okay, I've also included some decimal places there, so hopefully it won't be too much. And what else do we need to know? We're not going to use the time, because that's the time that the alpha particle will need to actually go through to the other side of the plate, which it doesn't make it. Okay, so we need to find the time it takes for it to land to the other side of the plate. So we need to know the t value. Okay, so since this is like a 2D projectile motion question, let's set it up like a 2D projectile motion question. So the x coordinates and the y coordinates. The y coordinates we know A already, which is given. Okay, so I'm just going to put a check mark so I don't have to write it again. Sorry, I'm a little lazy. And then the horizontal velocity here, which is also given to us. We don't know the time, and time is often the connecting factor between the two directionalities. So there's also that. We also know that the vertical drop here is going to be 0.4 centimeters, which we'll have to convert to meters, which is 0.004 meters. So there it is. We also know that the particle does not have any initial vertical velocity, because it's like free fall. Okay, it's only shot horizontally, so it doesn't have any vertical velocity component. Okay, so with that matter, I think we can figure out t from the vertical side. Okay, oh, and last but not least, the one that we don't know is we don't know this, it's like the range. You're kind of finding the range, how far it travels horizontally. So actually it's called d, not sx. So I labeled as d, so we'll call that d. Okay, so let's go ahead and solve for t, and we're going to use this one because we know that the initial velocity is 0, so that term goes away, just like I showed us in the previous question. So to solve for t, I'm going to do this all in one step, guys. T is going to be equal to 2 times s divided by a, and then taking the square root because it's t. Okay, substituting all of this in, we're going to get square root of 2 times s, 0.04 meters, divided by the acceleration, 3.6 times 10 to the power of 12 meters per second squared. Okay, so that time we're going to get, I get 4.7 ... times 10 to the power of -8 seconds. Oh, just shy of 50 nanoseconds. That's too bad. So we're going to need this time here. So we got this time, So we're going to need to substitute this time. We're going to use it with that horizontal velocity to figure out the d, sorry. And we know that with constant velocity, we can use d is equal to vx times the time. So that's going to be 480,818 meters per second times the time, which is going to be 4.7 ... and everything's stored on my calculator here, minus 8 seconds. Okay, so we do that multiplication. I get 0.02266, and that's going to be in centimeters, that's going to be 2.26 centimeters. Run it up to 2.3 centimeters. Oh, it was so close. It was so close. So basically, in this previous diagram, the total distance was 2.4 centimeters. It's going to make it just there before it can make it through the plate. So it just misses the end of the plate there. Ha ha ha. Poor thing. Okay. So there we go. That was the first question. Second question is B. A magnetic field is applied on the section containing the parallel plates so that the alpha particle is able to move directly straight across the plates. What is the magnitude and direction of the magnetic field? Well, first of all, we know that because of the electric field lines, the electrostatic force acting on this alpha particle is downwards. So in order for this particle to make it across, it needs to experience an equal and opposite force in the opposite direction, which might as well be the magnetic force, since we're going to apply a magnetic field, right? So let's work out the magnitude first, because we know that the magnetic force, which is QVB, is going to be equal to the electric field, which is going to be Q times the electrostatic field. Okay, we'll add vectors here to show these are all vectors. Okay, so because these are equal, the Q's immediately cancel out. So it doesn't really matter what the charge is. And we're left with electrostatic field is equal to VB. So let's solve for B. We're going to solve for B by dividing both sides by the speed that this particle is going at, the alpha particle is going at. So B, the magnetic field, is equal to the electric field divided by that speed. The electric field we found in the previous question, which was 75,000 Newton per Coulomb. And the speed we found was, we're going to use the one here, which is 480,818. That was the speed we found earlier. 480,818 meters per second. So let's figure that out first. Okay, so I get 0.15598, so that's going to be equal to 0.16 Tesla. Okay, so that's the magnitude. We're not done yet. We still need to figure out the direction of this. So since we're going to use our right hand rule, and this is an alpha particle, has a positive charge, so I'm using my right hand. You're going to see me as using my left hand, or some weird mirror effect. So if I am, so using the right hand rule, my hand's going to look weird, but to you, hopefully. But I'm just going to talk about fingers. Thumb is going to be the direction of the movement of the charged particle, so that's the alpha particle. Take your right thumb and point it towards the, on your page, it's going to be towards the right side. Okay. In this case, we don't know what the the magnetic field direction is going to be. So we don't know what the direction of the index finger is going to be. So we'll talk about that later. The middle finger is going to point in this way, so it's going to point towards the direction of which the magnetic force, the direction which you want the magnetic force to be in. So in this case, it's going to be upwards. Okay, upwards. It's going to be upwards to the positive plate. So if I'm doing this correctly, my thumb is towards the right. My force is up. My field has to be into the page. So this has to be into the page. My magnetic field has to be into the page. So I'm going to write here into the page. That's going to be the direction of the field. Magnetic field needed. Okay, so I've got the magnitude, I got the direction of this field, and voila, there was a question. The math wasn't too bad. The previous question was a more elaborate for sure. Okay, so, well, if you made it this far in this video, thank you so much for watching. Hopefully the bonus questions really helped you to exercise your understanding of this unit, as well as applying the other units back in again, like kinematics. So job well done. I thank you for watching and bearing with me in this video. I wish you the best of luck, and Fan Mama Physics signing out.